Round number 35. A group of researchers in Washington University School of Medicine develop a new food supplement that should lower blood cholesterol. They select a random sample of 10 volunteers and record their cholesterol before and after the treatment of taking the supplement. We know that cholesterol levels are normally distributed. Perform a test to see if there is enough evidence to say the new food supplement lowers cholesterol level. State the null and alternative, compute a test statistic, give a p-value, then use significance level alpha equals 0.05. So this is a matched pairs design. We've got two values for each subject, and we're wondering whether there's a change or difference in the values that, in this case, we want the second value to be less. So if we do before minus after, I'm hoping for a positive response across all the subjects, or at least on average a positive response. So here's before and after. I put it in my calculator in list 1, list 2, and then I didn't feel like subtracting them all by hand, so I did list arithmetic. I went L1 minus L2, stored in L3, and L3 popped up looking like that. And then I went in there to L3 and asked for the mean of standard deviation with one variable statistics. I got 14.8, 20.62. And I got curious about the distribution. It says here, we know that cholesterol levels are normally distributed, but really we would need the change in cholesterol levels to be normally distributed, so we need these kinds of values to come from a normal distribution. There's only 10 of them, so it's going to be pretty hard to tell if they're normal. A lot of times things you collect in nature are more or less normally distributed, so you want to see if there's evidence to refute that. So I decided to make a histogram using classes of width 10. And here are the counts in the different classes. I went minus 10 to 0, 0 to 10, 10 to 20, 20, 30, 30, 40, 40, 50, 50, 60, 70, and then there's a boundary value problem. So I went up to 0 not including 0, up to 10 not including 10 as to take care of that boundary problem. I got this graph. As it says, the t-test might not be valid because it's not symmetric. It is kind of single-peaked. It does maybe have an outlier. It says, but the outlier is not extreme, and if you take that outlier into account, maybe skewness is slight. So it isn't a game changer for saying I just can't use t. Just might want to take some caution in the results because it doesn't meet the criteria exactly. The sample size is small. It's not evidently a bell curve. Data like this does come from normal distributions, but usually if you have 10 values you might see something slightly better, but it's not too bad. So then we go and set up the hypothesis test. We call these things differences. Sometimes we call them D for differences. Okay. And so this D here says that would be the long-term mean of those differences. So what that says is you would take many subjects, record before and after, take the difference, look at the mean for many subjects. Would that mean most likely to be 0, or is it likely to be greater than 0? That's what we're testing. And then we compute a t-statistic. It's x bar minus the mean, which is 0 here, over s over root n. I get 2.27. That's usually pretty good news. I go to degrees of freedom 9. N was 10. There's n values in this difference column. And so the degrees of freedom is n minus 1 for t. So I go to that degrees of freedom row. Here's what it looks like with degrees of freedom equal to 9. We're looking for 2.27. I got 2.26 and 2.39, so below it and above it, pretty close to it actually. And p-value 0.05 there and 0.04 here. It's a one-sided test. One-sided because of this. And so we'll say the p-value is between 0.05 and 0.04, so just a little bit less than 0.05. When we go up here to the conclusions, p-value is less than 0.05, so we reject the null hypothesis. So we need the p-value to be smaller than 0.05 to reject at the 0.05 level. Does it say use the 0.05 level? If it doesn't, I just use it anyway. It says use the 5% level. Okay. So the medication seems to work. In these cases, sometimes it's convenient to create a confidence interval for how much effect the treatment has. That would be a way to estimate the mean, the long-term mean. We know it's probably not 0. So I made a confidence interval like this. And here's the range of values that are possible. It says the long-term mean might be less than 0 by, or actually greater than 0, that it might be 0.05, or it could be as big as 29.54. Now probably changes as small as 10 aren't very meaningful. I don't know, I'm not a doctor. But changes as big as 30 might be. So that's the range that the medication might produce long-term. So from 10 individuals, it's pretty hard to tell the strength of the effect. And most of that effect is, again, probably due to this 60 showing up in the data set. And so we'd have to show some suspicion that maybe the effect really isn't that great. If it only, for 9 out of 10 people, the impact was not that great. It's just the one value, that 61, that might have pushed us over the edge, both into statistical significance and also giving this upper bound of 29.54. So that, no, the t-test might not be valid, and then we look to see what we have here for a confidence interval, and we think about how close to the 0.05 level we are. We might say that we're hesitant to reject the null hypothesis based on those kinds of observations, and we don't know the strength of the effect of the new supplement. And that our conclusion would be to the researchers that they should do a larger study. There's still a reason to think this might work, but you're going to need more subjects. A larger study, maybe go with 40 or something like that, so you have more of an idea of exactly what's going on, because that standard deviation is big in terms of what the treatment impact is. So you want to see what the average impact is. You need a larger sample size to narrow down the size of the confidence interval and make us more certain that when we reject the null hypothesis, we're believing what we said. So that's 35 in all its glory, a t-test. But first we have to subtract values because it's matched pairs, and we have to look at distributions. A histogram is one way to do that. And then even after we reject or fail to reject the null hypothesis, it might be prudent to make a confidence interval and see what it tells us. And that really is part and parcel, as they might say, the conclusion of our class, where you can actually take data, analyze it, and produce two different ways of looking at the results where you can draw conclusions. One of them is the confidence interval, and the other one's hypothesis testing. And there we go. Another slide down.